An inverted pyramid is filled with water at a constant rate of 45 cubic centimeters per second, and the pyramid at the top has a shape of a square with side lengths of 3. So at the very top, these are 3 centimeters, and a height of 7 centimeters. And we want to know what's the rate at which the water level is rising when the water level is at 3 centimeters. So one thing we can think about is the shape of this pyramid. If we're filling it with water, when we first start filling it, the amount that it holds at the very bottom is very small. So when we start filling, it's going to rise up very quickly. But when we get closer to the top, it's going to be a lot more spread out. And so the rate at which the height of the water is going to change is going to be a lot more slow. And so this is what it's asking for, is we want to know what is that rate when we're at 3 centimeters up. So as we approach any of these types of problems here, what we're often going to start off with is just thinking about what are all the pieces of information that's given, what are all the relationships between these values that we can come up with, and then we can come up with a plan that's going to link all these things together and start plugging them in. So let's start off with that. Let's put all the pieces of information that we have here. So the first thing we have is maybe we might want to remember that there is a volume type of formula here, and that's 1/3 base times height. And so this will be useful in connecting the volume, which we know we're filling at a rate of 45 cubic centimeters per second. So what does that tell us actually is the amount of water, the volume that's being held is changing. The amount of water, the volume dV dt, that rate of change is actually that 45 cubic centimeters per second. What else do we know is the pyramid at the top has a shape of a square with side length 3, so we already kind of put that into the picture, as well as the height of 7. And finally, we know that we're going to be interested in the rate of change when our height is specifically at 3 centimeters. So as we're trying to think through this, one thing that we notice is that the volume, we need to somehow get that related to what dH dt is, because that's what's missing. We want to know how quickly is the h changing with respect to time. So this is our unknown. And hopefully we see that, okay, this volume equation here is going to be useful to us, because if we take the derivative of it using implicit differentiation, we'll have our dV dt coming from here, and we'll have our dH dt coming from here. But there's some other things here that we need to kind of fill in that's missing. So let's see if we can figure those things out together. One of the things that we're going to need is this base. So if we were to talk about this entire thing, yeah, the base would just be 3 times 3, it's a square, would be an area of 9 square centimeters. But we don't know what the base is at any given level, right? Because here we actually have a different base. We have that it's going to have this square shape again, but it's going to be smaller than that 3 by 3. So since we don't know that, let's call that S for now. But it's going to be the same S because it is a square. So what we need to figure out then is how can we figure out the S, the value of S, the side length, when we know the height of the function? Is there any relationship that we can make with that? Maybe one way we could do this is we should recognize that these are similar shapes. And so perhaps we can use a proportion to kind of make that up. So one thing that we know is that if we were to compare S to H, right, the side length to the height, right, in this case it's 3, but again, it could be any height. Well, one thing that we know is it's going to be proportional. So why don't we just use it as in proportion to the entire thing? Well, the entire thing has a container base side length of 3 and has an entire height of 7. So we can use this proportion and find that there's a relationship of just multiplying by h, S is equal to 3 over 7 times h. And so here is a relationship that we can also come up with based on the information that's given. Now, one thing that we're going to notice is, again, we're going to need to know dH dt. And if we did try to figure this out, you're going to notice that we're going to have to use this in this case too. So a lot of times once we have a relationship between two variables, those related rates are also important to us. So if we take the derivative of this with respect to t, we get ds dt is equal to 3/7 dh dt. So this will be very useful to us as well. Maybe one last thing of what else information can we get is this base here. Well, where does that come from? If I needed to know what's the area of the base to plug this into the formula, it's just the side lengths, right? So in this case, it would be s times s, or s squared. So another way of writing this formula would be 1/3 s squared times h. So these are all the pieces of information that we've got. Once we have those things together, again, what we can do is kind of what we did right here with the main connection is let's take the derivative and then see how these rates are related. So I'm going to take the derivative of this v equals, well, not that one actually, this one here, because we have s instead of a base. So if we take the derivative, it's going to give us dv dt is equal to 1/3. And then here I have s squared times h. So we're going to have to apply our product rule here. And so let's be very careful of that product rule. So if I take the derivative of the first part, this would give me 2s. And again, we're doing this with respect to t, so using the chain rule, we have to go times ds dt, right? Because we're using implicit differentiation. And then we still have the first part times the second, so that would be times h. And then plus the derivative of the second part. So the derivative of h is just 1, but again, using our implicit differentiation, our chain rule, that would be dh dt. 1 times dh dt is just dh dt times the first, so times s squared. So let's see, with this relationship, we see that we have a dh dt, we have a dv dt, right? So by knowing those things, then we can solve for dh dt, but we have some other information that we might need to go back and try and figure out as well. So for example, s, do we know that s, well, we don't have it here, but remember, we're specifically looking at when h is 3. So we have a way of actually figuring out s. We found that out earlier right here. So let's get what s would be when h is 3. So if h is 3, then s would be 3/7 times h, which should be 9/7. So now we have something to plug in for s. ds dt, we know we're just going to plug in this 3/7 dh dt. We have our h is 3. We have a dh dt again, which is our unknown. And then we have our s, which is again the 9/7. So we have everything we need to plug in, and then we can solve for dh dt. So let's go ahead and start substituting all those values. So we know the dv dt is 45. We have 1/3. I have 2 times s, and again, our s that we're using when h is 3 is 9/7. We have ds dt, but again, what are we going to put in its place is 3/7 dh dt. And then we have times our h, which again, the problem specifically told us use an h of when we want to know when h is 3. We have plus dh dt again times s squared, so 9/7 squared. And so we have everything substituted. The only thing that's left that we need to solve for now is our dh dt, right? That's what's our unknown. That's what we're trying to figure out. How quickly is the height changing with respect to time? So with that, we can go ahead and just solve for dh dt. So maybe I'll simplify this a little bit and factor out that dh dt. So I have 45 is equal to, I'll pull the dh dt out of both of those, dh dt in front, times 1/3. And still inside, we have 2 times 9/7 times 3/7 times 3. And here I still have the 9/7 squared. So let me multiply all that out on a calculator. Right? So using Desmos, I see I get 81/49. So this would be 45 is equal to 81 over 49 dH dt. And of course, then to solve for dH dt, we can just multiply by the reciprocal. So this would give me 49 over 81 times 45 is equal to our dH dt. And multiplying that out, that gives me 245 over 9, which is about 27.2. And this is in centimeters per second. All right, so to recap this whole problem, again, the key thing to always start off everything is just to write down as much information as you can and as many relationships between variables as you can. Then when you take the derivative, sometimes in this case, we saw that, hey, there's some variables that are in my derivative that I need to know the equation or need to know the values of. And so we had to think back, is there any way of figuring those out? And so we did see, oh, yeah, we could do that using these proportions. And so then once we have that, we had all the values of every single variable to plug in, and then we could just solve for our variable dH dt since that was the unknown. Hope that helped.